In this video, we're going to talk about shear distribution in thin-walled members. And so by thin-walled members, we're particularly going to look at open type members, so things like I sections, T sections, C sections, and that's really what we're looking at. So one of the questions is, well, how thin is thin? And we'll get to that sort of towards the end of this lecture. But this will help us, particularly for if we want to analyze things like the distribution of shear in a built-up steel section, which might be like a steel box section or a welded steel I section. So with steel, oftentimes you'll just go essentially to a catalog and buy a standard size. But you might have, for example, if you are designing a bridge beam and that you need a really large, very deep, very stiff beam in order to make the span crossing to work, and in order to keep your stresses down and your deflections small. Well, you might have to design one and then have it welded up out of pieces of steel. So what we'll learn over the next few lectures will help sort of cement some of those ideas. But before we get too far into that, it's good to do a quick recap of what we've learned so far about shear in beams. And the reason that we're going to look at this is that, one, we've thrown a lot of material at you over the last few lectures, and two, it will help sort of if we go back over some of the things that we've learned, it should make the concepts we're going to need for determining shear and thin-walled members make a bit more sense. So with that, let's look at the very first thing that we looked at is shear stress, just taking it as an average stress. So the shear divided by the area, and we found it doesn't work so well. This average stress works well for, say, tension members, where we have the tension force divided by the area, but not so well for shear. With sort of two exceptions, we found that for bolts it worked pretty well, at least in terms of the forces that these bolts are likely to see while they're getting used, as well as providing a useful design criteria. We found that bolts and shear, just taking our shear force divided by the area of the bolt, were reasonable approximation. And just to sort of reiterate, remember we had our single shear where we had just one shear plane, or we had double shear where we had two shear planes. The other place where we found that it worked fairly well was for if we're determining the shear stress in the web of an I section. So I'm going to say this. We will go back through. I hope that doesn't confuse you, because we will sort of revisit this distribution when we look at thin-walled sections. But in terms of if you're, say, designing a steel beam, you'll find that a lot of steel codes around the world allow you to just determine your shear stress based upon the applied shear divided by the area of the web. And that's because the area of the web, and we did an example with this, we found that the area of the web, that was taking about 95%, 96% of the total shear stress and the total shear force within the section. So for design, where we need to be able to iterate quickly and we want to use simplifications which get us pretty close to the answer, this is a good one. Now, as I said, as we progress through this lecture and the subsequent ones, we're not going to use this. But just wanted to sort of reiterate that for design, it's not a bad use, but for when we start looking at what our actual shear distribution is, particularly if we're trying to size, say, welds, then we need to use a different method. All right, so that was sort of the first bit that we looked at. It was just sort of looking at average shear. The second one is we went through, we did a small derivation, and we found out that for any little, say, block of material, with some distance, dx. We found that our shear forces, both longitudinal and perpendicular, have to be equal. And that's for rotational equilibrium. If we took some moments right about the center, because these are all the same distance, in order for this block not to be rotating around, our longitudinal shears have to equal our transverse shear. And it's that, tau xy has to equal tau yx. If we extend this concept where our longitudinal and our transverse shears have to be the same just a little bit further, we can see that, well, if we're right on top of a surface, that we actually don't have any shear stress. And that's because, if we take our hands together, in between my hands, they're trying to shear across. So there's that, because my hands, it's friction. If it's a if it's a beam, it's going to be the molecular bonds between the different portions. But in between we've got shear. But on my knuckles here, well, that's just going against air. There's no shear there. And I mean, you can do this yourself. If you push your hands together and then try to move them apart, well, you'll feel on your palms that you've got some stress, and you can feel that there's something working there. But on the back of your hands, you can feel, well, there's actually there's no stress there. And that's the same thing here. So because our longitudinal stress is 0 right at the free edge, while the transverse stress at that very, very small little piece dx, that also has to be 0. So we know that at the the edges of our, so that's sort of top and bottom edge, if we have a force pointing downwards, we know that those shear stresses have to be 0. So, looking at our sort of last part of our recap, if we take the points 2 and 3 and we put them together, well, this is how we derived our shear stress distribution for a beam with a transverse load. So, say that we've got our little beam here. I've got a transverse load. Here's our shear and our bending moment diagrams. Well, we took a little section, and say we took it, here and here. So because we take this little tiny slice, we'll say that slice is dx. Well, because we've got a change in moment, which we by definition need, if we have a shear, well, then we have a change in moment. You notice, if you draw your shear and shear force and bending moment diagrams, if you have a constant bending moment, well, you've got no shear. So if we have shear, we have a change in bending moment with respect to distance across. So if we take this sort of little block out of the beam and we draw it over here, we can see that on one end, it's got a bending stress sigma A. And imagine that this height here is going to be half the depth. So we're right at the neutral axis. So we're going to have the full compression block from our bending stresses pushing in. And then on the other side, well, it also has the compression block, but it's a little bit more because we have a slightly larger M. And remember that, if our bending stress equals my over I, a slightly bigger moment, a slightly bigger bending stress. So in order for this system to be in equilibrium, because currently, if we ignore the shear stress, well, this little block wants to push this way. But because it's the beam is static, it's in equilibrium, it has to have a force which balances it out. And that's this longitudinal shear force. Well, that's good. So if we sum sort of the forces along the lines of the beam, we have, the sigma A times this area plus the shear stress tau times this area is going to equal this shear stress plus this extra little bending stress from the extra little big moment over here. All right, and then again, because we've got our longitudinal shears and our transverse shears have to be equal, what we found out over here, Well, we're going to have this shear stress tau going longitudinally. We'll also have it going transversely. So because tau goes this direction over here, well, tau is going to go down over here. And because going this way over here, well, it's going to go up over here. So just pause and take a little moment and just sort of get this idea in your head. And have a look at the diagram there, because this is really the key to how all of our shear stress works. It's a difference in bending stresses which act along the length of the member, and so it's the longitudinal shear force. So we always think of shear as transverse, but it's really the longitudinal shear force which is balancing this out. And then just because equilibrium has to be satisfied, do we generate this transverse shear? So with that in mind, this also sort of brings out one of our other sort of truths about shear stress, which is that the shear stress has to be a maximum at the neutral axis. And that's because if our bending stress, maybe I can draw our bending stress over here by our stress equation. Remember, our bending stress is going to vary linearly. It's going to be 0 at our neutral axis because at the neutral axis, the material doesn't stretch or compress. So there's no strain there. So this is going to be our sigma in compression, our sigma in tension. And you can see that, well, if what we're doing is really just trying to balance out this, this sort of stress block here from one side to the other, well, it's right when we get down to the neutral axis here that we have sort of the maximum force that we'd have to resist against. And to sort of, if we look at this element here, if we went further and we got into the tension zone, well, now we've got a little tension force pushing back here, so tau doesn't have to be as big. And so that's why at the neutral axis, our shear force is going to be a maximum. Sort of final two pieces to look at here on our recap was then, using all of this, we went through and we derived what our shear stress distribution is down the height of a member or of a section, and it's this VQ over IT. And remember that Q is just the big Q. Is just a shorthand for. So if we're looking at shear stress at a distance y away from the neutral axis, Q is just going to be the area of the section above that neutral axis. So it says A1 is that area, and Y1 is going to be the distance from the centroid of this area to the neutral axis of the section. So that's shear stress with distribution. We also looked at shear flow. So with shear flow, very similar. It's essentially, this equation here got a little bit messy. Let me just sort of rewrite that. You can think of shear flow is equal to tau times the thickness. Shear flow is just the shear force. So over here we're working with shear stress. Remember, stress is a force over an area. Shear flow is just going to be a force over a unit length. So for if we've got our little block up here, we've drawn it in stresses up here. If we're looking at a shear flow for some distance 1, and that could be, it's a unit length. It could be 1 millimeter, 1 inch, 1 meter. This is, the only thing we've got to look out for is our units, and just stay consistent. Well, if we're looking at the shear flow of, say, this little piece up here, instead of stresses, it's going to be forces. So we've got the compression force from this side, the compression force plus its small little extra component on this side, and then a shear force, which balances, these two forces out. So this shear force V is going to equal DF. And then because the block has to be in equilibrium, we got a shear force pointing down and a shear force pointing up. So that is, in essence, our review of what we've learned already with stress. So keeping that in mind, let's go back and revisit the shear in an I section. And So what I've drawn one up over here, and so well, let's have a look at it. What do we know? So I've drawn also the shear stress distribution. This is the shape that we've seen in some of our previous examples. So based upon the shape, well, and based upon what we know from our model here, we're assuming that basically we've got some shear stress, pointing down along the web like that. And also, we've kind of assumed that the flanges also have some shear stress pointing down. All right, so let's sort of go through and confirm or deny whether the way we've modeled this makes sense. So, what's our first one? Well, we know that tau max occurs at the neutral axis. We'll put a little checkbox there. So is that the case? Well, the way that we've drawn this out using our VQ over IT model, where Q is going to be its biggest is where, really this longitudinal force is the largest. Well, that's the neutral axis. So yeah, that's kind of what we've drawn there. So I'd say that's good. We've got, one of our understandings of how shear stress works. That works with our existing model. Now, the next thing we know is that that our shear stress varies parabolically with depth. So, that's let's have a look here. And again, we've kind of seen that from one of our previous, it varies parabolically with depth. We've kind of proved that, particularly for here in the web. So I'd say, that's still a pretty good way for how we've modeled this. And I'll just sort of reiterate, this model is based off of our tau equals VQ over IT, just to kind of, keep that in your head there. So let's have a look at sort of the last 2 points, and then we'll have a little discussion whether they make sense or not. So we know that our vertical shear stress has to equal our longitudinal shear stress. So that goes back to this tau yx equals tau xy. So, you remember our little model here, and I'll draw our shear stresses in red. Remember, that's there for equilibrium. That's this rule right here. So we've proved that has to be correct. And we also know, using the same model, that tau equals 0 at a free surface. And so you can think of free surface as kind of like a top or bottom, or you can also think of it like an edge. So, well, let's look at these last two. This is kind of where things fall apart a little bit. So the way we've drawn this, if we sort of zoom in on this flange here, we're assuming, based upon how we've done these calculations so far, that, we've got a shear stress which is going down in the flanges. Well, for that to be true, and for this part to be true, well, then we need to have a shear stress going along the edge. Well, then that violates this rule that, our tau equals 0 at a free surface. Well, that doesn't, that no longer holds true. So either these rules are wrong or we've have our model incorrect. And so I'll just tell you the answer. It's really, our model is not right here. We're not too far off, and the way that this has been laid out works well for thick sections, but for a thin section, it doesn't really hold true. And so what we're going to look at now is, again, sort of when in doubt, we're going to draw a free body diagram, and we're going to see what our how all of this lays out. So let's find out where our issues are. So, so before I go any further, remember here, it's really the flanges which are the problem. Here in the web, we're okay. If I'm to kind of draw our shear stress here. So that's at the neutral. That's an axis. That's going to be our biggest. Well, that's all right. I mean, we can continue to take, cuts through the neutral axis, cuts through the web, draw a free body diagram, and this whole thing is in equilibrium. So we say, the web is okay, It's the flanges that are the problem. All right, so let's figure out what's our correct model then. So if the web works all right, how's our flanges work? So maybe because tau equals 0, well, maybe there is no shear stress in these flanges. Well, let's have a look at that. Let's see, let's work through that and find out, well, is that a good model for us or not? So, option 1, shear in the web only. So we'll just draw our little picture. It's always helpful to have a picture to kind of visualize things. I mean, mathematics and equations are nice for proving stuff, but I know personally I always struggle just taking that direct leap to the equations for understanding. I always like a picture. Picture kind of reminds me of that we're working with something which is real. All right, so our first first option for trying to solve this problem where our longitudinal and our vertical shears aren't working in the web, and that we've got zero stress at our flanges, is that, maybe in order to make this one work, it's just there is no shear stress in the flanges, and there's only shear stress in the web. So there'd be in order for this to work, there's got to be, some force, F plus dF, and F, and this has some distance, dx. So just, we're really just trying to set up a very similar model to what we set up over here. So now, if we stop and we think about this model, there's a bit of a problem. And it comes really with the fact that, shear only occurs if there's a change in moment over length. So, I mean, that's worth writing down. Shear So so I mean that's true. Remember, go back to our shear force diagram. We only have shear because our moment is changing. So that's going to be the same as saying V equals change in m with respect to change in x. Well, if we go back to sort of our little free body diagram. So if this is our little distance, dx, and if we say we look just up here in the web, just up here, well, we know that we've got some bending stress up in the web, just sort of, by definition. I mean, that's what we know we've got bending stress up there. Well, and because we've got a change, well, instead of, so that's going to be our sigma, and this is going to be our sigma plus delta sigma. So if we draw the resultants here, sort of resultant for, you can think this is F and this is F plus dF. Well, currently this is out of balance. The only way to balance it is to have a shear. So that means that, well, even if we're looking just at this very top, we're not even looking at the web, well, there has to be a shear here. So, So there actually has to be shear. In the flanges. So because we've got bending stress in the flanges, well, there has to be a shear in the flanges. And so, well, that means that, well, this isn't a very good model either. We're kind of striking out where this model didn't work. It was okay for the web, but not good for the flanges. Assuming there is no shear stress in the flanges also doesn't work because we've got out of balance bending stresses there. So really, the only option is that there is shear in the flanges. But the orientation is wrong. So, if that's the case, well, let's have a look, and see, maybe again, if as you can see, I always think, well, if we draw a picture, we draw a free body diagram, well, that should hopefully help us figure out. I mean, that helped us figure out what was going on the web. Well, let's try it with the flanges. So. So if we take a free body diagram of the flange, let me just draw that out here, and I'll try to draw it with the extra, well, so with the rest of the section on top there, just so you can kind of see where we're taking the cut. So that's our little piece of flange there. And we're going to just cut that right out of the rest of the section. All right, so we've just taken our free body diagram of just this web over here. So what are the forces on it? Well, we know that it has some bending stress applied. And we'll just assume the top is in compression. And because it has shear, we know that there has to be a difference in bending stress across the length of the member, just by definition. So, we can say the magnitude of this stress is going to be sigma plus delta sigma, and that could be sigma. And in order for this to be balanced out, well, there has to be some shear stress along here. So say we take this, bring it over here, and just draw, so say we take that, and we bring it up over here, and we just draw it as a big block. And we just draw it as forces coming in. We'll draw those in red. And in fact, we'll even just dash in the back side of this block and give you some axes here. X, Y is pointing up, Z is pointing to the left. And so we've got some stress coming in, sigma. We've got some other stress, sigma plus delta sigma. In order for this to be balanced, well, there has to be a little shear stress here. That'll be tau Zx. And there's got to be a little shear stress here to keep this from spinning. Now there's no shear stress on the top, no shear stress on the bottom, and no shear stress over here. So the magnitude of this is going to be dependent upon really just the distance around. So and what we find, so that's tau x z, that tau x z equals tau zx equals our little sigma x. So, well, that will solve our equilibrium problem, and tau top equals 0. Again, that solves our other problem. So we've got this figured out now. So really the conclusion is that shear moves along the flanges. So our problem with our original way we were looking at the problem was we were assuming that the shear, and this is really true for thin wall sections. I want to really stress and reiterate that we were assuming that all our shear was moving up and down. It was moving across. And really, what it is our shear moves along sections. So when those sections are oriented in the direction of our load, so like with our web, the shear is going to go up and down because it's moving along that section. But for our flanges, well, it needs to move along in order to ensure that our shear stress equals 0 at our free edges. And so, if we kind of draw this out, and what our shear stress distribution looks like. So, because we said that it was going to flow to the left over here, so we'll just bring that up here and just, got a little shear going that way. Well, we're going to have some shear moving this way. Kind of from symmetry, if we do the same thing, but we come from the other side, we'll see that our shear is going to move in towards the center and then down, and we'll work this out with some free body diagrams here in the moment, but basically you see that our shear flows through the section, so shear flows through the section. And you can kind of think about it, analogous to like water in a pipe. So, the water's going to come here, and then you want to come back out and sort of fill up through here. So if our load's coming in from the top, it's going to flow out and around. And so because our shear flows, and really what we want to find out is, as we continue to move across our flanges from the edge, well, how does this shear force grow? Well, if we want to see, what our shear is over a given length, well, then we want to use our shear flow equation. And so, this is going to be, Q equals VQ over I. And this is really going to be the sort of the governing equation for what we want to have as we're looking at these shear flow problems in thin wall sections. So just sort of keep in mind that instead looking at a shear per unit length, along so instead of looking at it along a member like we did when we were looking at shear flow for sort of determining the shear force on nails of a given spacing, we're going to look along the section. So we're really, it's the same thing. It's still a shear force per unit length, but instead of going this way down the length of the member, we're going to be going along the member, from the edges. So that's essentially going to be what our what we're going to be doing over these next few lectures is working with determining our shear distribution in these thin wall sections using shear flow. Now, just a real quick aside. So the way I've drawn this as it's coming in, left and right, and then coming down, you can notice that the shear stress or the shear flow, shear direction changes top to bottom. So left to right, I think we can look at this where if we flip this free body diagram, you can work out that, okay, well, if shear's got to go this way, is it going to come this way longitudinally? Well, it's got to get, so on this side, if you had a, shear coming this way, well, you'd have to have a shear going that way in order to balance it out. But, why does it flip top to bottom? Why isn't it just like this? Well, it's because, if we're bending, so if this is our neutral axis, if we're bending it where there's compression on the top, well, our direction of force changes on the bottom. So say we take a little block at A. So at A, flange is in compression. So, and this is assuming that we've got, a simply supported beam like that. So that little block there at A is going to have, sigma plus d sigma, tau has to go towards the compression block, and so tau is going to go to the right. So if we then take another little cut, same distance away, but we just look in our bottom flange, with B, which is in tension, we draw our same little block here, but this time, well, if we bring sigma plus delta sigma this way, sigma that way, well, in order to balance this out, our shear force or shear has to change our directions, and that means that tau on the face changes directions as well. And that's what you see. We're on the top, we're going this way because we're in compression, and on the bottom we're going the opposite way. So that's essentially our introduction to this topic of shear flow in thin wall sections. It's a little confusing at first, but hopefully with this lecture you can see that it really does all just break down to equilibrium equations, free body diagrams, and that once you can if you can keep these visualizations in your head, it means that following the rules aren't just arbitrary. You can tie them back to a physical behavior. So that's where we're going to wrap up for this lecture. I hope that was informative and kind of shows some a nice, elegant way for understanding how this shear moves around the structure. And so what we're going to do is in our next lecture is we're going to work again with an I section, and we'll do an example kind of with no numbers, but again to kind of sort of prove some of the rules that we will see for if we want to solve more complex structures than just an I structure. So with that, thank you very much.